A dog breeder needs at least 6 units per day of nutrient A and at least 3 units per day of nutrient B for her beagles. And that breeder can choose between two different feeds, feed 1 and feed 2. Each bag of feed 1 costs $3 and provides 1 unit of nutrient A and 2 units of nutrient B. Each bag of feed 2 costs $2 and provides 3 units of nutrient A and 1 unit of nutrient B. How many bags of each type of feed should be bought to minimize the daily cost? So like most of our linear programming problems, there are a lot of information here, so we're going to follow that basic strategy that we've talked about in earlier sections to come up with the linear programming problem. So I've gone ahead and kind of made my problem a little bit smaller, and the first thing we'll do is we'll look for the variables. The question asks how many bags of each type of feed. So Y1 is bags of feed 1, Y2 is bags of feed 2. I'm using Y1 and Y2 because I noticed that it said minimize here. So now that I have my variables, now I can go ahead and look for that objective function where it said to minimize the daily cost. I noticed that feed 1 costs $3 and feed 2 costs $2. So if I go ahead and connect my variables with those costs, I'll see that I need to minimize W, which is the cost, and that's 3Y1 plus 2Y2, because one bag of feed costs $3, so Y1 will be 3Y1, and the same thing for the other term. Now let's start looking for some constraints. It said that I need at least 6 units per day of nutrient A, and that feed 1 provided 1 unit and feed 2 provided 3 units. So I can take that information, put it together, and what I see is that my constraint is going to be greater than or equal to 6 because I need it at least, so that means 6 or more. And if feed 1 provided 1 unit in one bag, then Y1 bags will provide Y1 units. If one bag of feed 2 provided 3 units of nutrient A, then Y2 bags will provide 3 times Y2. So the total amount here of nutrient A is given on the left-hand side, and that needs to be greater than or equal to 6. We can do the exact same thing for our nutrient B. We needed at least 3 units of nutrient B, so my constraint is greater than or equal to 3. And I see that one bag of feed 1 provided 2 units of nutrient B, so Y1 bags will provide 2Y1. And one bag of feed 2 provided 1 unit of nutrient B, so Y2 bags would provide Y2 units of nutrient B. That gives me my second constraint. I'll also need to have my non-negativity constraints because these are bags, and so I've gone ahead and added that in here. So now we need to go ahead and find the dual problem. So just like we did before, I go ahead and I write out this new matrix. The first 2 rows correspond to our 2 constraints here. So we had Y1 plus 3Y2 greater than or equal to 6. So I have a row here, 1, 3, 6. And I have the second row, 2, 1, 3. My objective function was W equals 3Y1 plus 2Y2, so the last row is 3, 2, 0. Now we need to do the transpose. So when I take the first row, put it in the first column, the second row, put it in the second column, and the third row, put it in the third column. So that gives me the numbers that I now need for my standard maximization problem. So when I write that out, the 630 in the bottom row tells me that I'm maximizing z equals 6x1 plus 3x2. The top row, 1, 2, 3, tells me that I have a constraint x1 plus 2x2 less than or equal to 3. The second row, being 3, 1, 2, tells me that 3x1 plus x2 less than or equal to 2. And of course, since this is a standard maximization problem, I have the non-negativity constraints. I'm using x's instead of y's, z instead of w, and now my constraints are all less than or equal to instead of the greater than or equal to that was on the minimization problem. There are my dual problems. Now that I have my standard maximization problem, I need to go ahead and start my simplex method by coming up with my initial simplex tableau. So in the objective function, I put everything on the left-hand side, and that leaves me with the bottom row in my simplex tableau being minus 6, minus 3, 0, 0, 1, 0. I'll add in to the first constraint plus S1, and when I write that in my simplex tableau, the first row becomes 1, 2, 1, 0, 0, 3. And when I add in the slack variable S2 to the second constraint, I get 3, 1, 0, 1, 0, 2. So there's my simplex tableau, and now I need to go ahead and find the pivot. So the pivot in this case comes from the most negative column on the indicator, so the negative 6 gives me that the first column is my pivot. And when I form my ratios, 3 over 1, 2 over 3, 2/3 is smallest, so that means the 3 is my pivot. So that's going to need to become a 1, so that means 1/3 row 2, put that into row 2, and that's what gives me the 1, 1/3, 0, 1/3, 0, 2/3. And then I need to go ahead and put zeros above and below, and I do that by taking negative 1 times row 2, add that to row 1, put it in row 1, and 6 times row 2 added to row 3, put that into row 3. So the first row becomes 0, 5/3, 1, negative 1/3, 0, 7/3, and the last row becomes 0, negative 1, 0, 2, 1, 4. And there's that nasty negative indicator, so that tells me that I'm not at my optimal solution yet. I've got a pivot column here where I see that negative 1. We'll need to go ahead and work out our ratios. 7/3 divided by 5/3 is 7/5. 2/3 divided by 1/3 is 2. So 5/3 is going to be my next pivot. So there you see it. So I need that to become a 1. So I'll take 3/5 times row 1, put that into row 1, and then I need to put zeros below it, and I'll do that by taking negative 1/3 row 1 plus row 2, put it into row 2, row 1 plus row 3, put that into row 3. And here's the matrix we get. The first row is 0, 1, 3/5, negative 1/5, 0, 7/5. The second row is 1, 0, negative 1/5, 2/5, 0, 1/5. And the bottom row is 0, 0, 3/5, 9/5, 1, and 27/5. I see no negative indicators, so now I'm at my optimal solution. Looking at the final tableau that I have here, the dog breeder will obtain the minimum daily costs if she uses 3/5 bag of feed 1 and 9/5 bags of feed 2 each day. When she does that, she'll come up with a minimum daily cost of 27/5 or $5.40. There's the solution to our problem. We get it from that maximization problem. We can also see, though, what the standard maximization problem solutions are. We see S1 and S2 are the non-basic variables, so we'd set them equal to 0. We'd get that X1 is 1/5, X2 is 7/5, and Z is 27/5. That's a solution to a problem, but what does this mean? So let's look at that a little bit closer. Let's take one of our constraints and use it to kind of in a backwards way figure out what X1 and X2 actually represent. So in that constraint, 1x1 plus 2x2 less than or equal to 3, that 3 was the cost per bag of feed 1. The 2 that I see in front of the x2 was the amount of nutrient B in each bag of feed 1, and the 1 is the amount of nutrient A in each bag of feed 1. So we have nutrients per bag times the variable, and that has to give us cost per bag. And the same thing with the other term. So what that means is x1 and x2, well, x1 must be the cost per unit of nutrient A, and x2 must be the cost per unit of nutrient B. Because if I take the amount of nutrient in each bag of feed 1, so that's the amount of nutrient B per bag of feed 1, and I multiply that times the cost per unit of nutrient A, when I do that multiplication, the units give me the cost per bag of feed 1. These are called the shadow costs. When I find out that what x1 and x2 are, I can use that to help me understand what's going on in the problem. We had that x1 was 1/5, so 20 cents or $0.20. So what that tells me is if the nutrient requirements for A were changed by 1 unit, the cost would change by 20 cents because this is the cost per unit of nutrient A. So an increase of 1 unit of nutrient A means that the cost would go up by 20 cents. Since x2 is 7/5 or $1.40, that means that if the nutrient B requirements were changed by 1 unit, they were increased by 1, then the costs would also increase by $1.40. So the shadow costs tell us that if some of the requirements of the problem are changed, then that tells us how the corresponding costs are going to change. And sometimes that's handy information to know.